with the disease. Deaths were rare in that group. The CDC had no information about underlying health conditions for this analysis. Richard Harris,
Iranian state TV says the supreme leader will pardon an additional 10,000 prisoners as the country struggles to stem the spread of coronavirus.
So start by letting you guys know that I have updated chapter 8 slides and I posted it yesterday, so I hope everyone had a copy of it. There's certain, basically what I did, I had to delete a couple of slides which I don't think was very necessary for us to go through. And I have also made a short video to distinguish between electron withdrawing and electron donating group. How do you distinguish if a group will be electron withdrawing or if a group will be electron donating? The video is posted on YouTube, and then I also shared the link on Blackboard. I highly encourage you guys to watch the video. It's a very short one, it's just 10 minutes, but that gives you a good amount of hints that will be necessary for the rest of the chapter and for chapter 18, especially for chapter 18. So I would really advise you guys to do that. Okay. So last time we ended our class talking about kinetics versus thermodynamics product. Okay. So in front of us here we have the reaction of 1,3-butadiene with hydrogen bromide. And this reaction is very similar to the reaction of alkenes, what we've seen before. But the difference is that we form two products. We have a 1,2 addition and we have a 1,4 addition. So the first thing is that we need to know the nomenclature. If you look at the structure of 1,3-butadiene, this is a carbon referred to as carbon number 1. This is carbon number 2, carbon number 3, and carbon number 4. Okay, and now when you observe the product, what you notice is that if you only focus on carbon number 1 and carbon number 2, that particular double bond, you will notice that we follow the Markovnikov rule. Carbon number 1 with more hydrogen ends up with more hydrogen, and then carbon number 2 ends up with the bromine. So this is a 1,2 addition product because you are adding a hydrogen on carbon 1 and a bromine on carbon 2. That's why we refer to it as a 1,2 addition. Then the second product is referred to as a 1,4 addition because if you notice from the nomenclature, you ended up adding a hydrogen on carbon number 1 and the bromine on carbon number 4. So that's why this is called a 1,4 addition. So that's the first thing I want you guys to take note. The difference between a 1,2 addition product and a 1,4 addition product. In a 1,2, you are adding a hydrogen on carbon 1 and a bromine on carbon 2. And in a 1,4, you are adding the hydrogen on carbon 1 and the bromine on carbon number 4. Okay. Now, generally, the 1,2 addition is referred to as the kinetic product, whereas the 1,4 addition is referred to as the thermodynamic product. First thing is that we need to understand what this means. We need to understand the terms kinetic and thermodynamic. And kinetics, basically, whenever we talk about kinetics, we are referring to speed. Kinetic has to do with speed. How fast can something be formed? So that's basically what kinetic is. So the kinetic product usually is the product that is formed the fastest. That's what we refer to as a kinetic product. Whereas the thermodynamic product always refer to the product that is most stable. Okay, so that's what I want you guys to keep in mind here. So kinetic product equals fastest form, whereas the thermodynamics equals most stable. So henceforth, Henceforth, whenever I ask you for the most stable product, whenever I ask you guys for the most stable product, I am indirectly asking you guys for the thermodynamics product usually. But then there are some situations, as we will see in the future, that the kinetic product is also the thermodynamic product. Does that make sense? So you need to keep that in mind. Now, my question is, if this is product A and that's product B, what makes B more stable than A?
The double bond is more substituted.
Because the double bond of B is more substituted. That's why B is more stable than A. Okay, let's recall that again, guys. Remember saying that whenever you're looking at alkenes, you're focusing on the carbon atoms that are involved in the formation of the double bond. And you will notice that in product A, you have a total of three. In product A, you have a total of 3 hydrogens connected to that double bond, whereas in product B, you only have a total of 2 hydrogens. So because B has a fewer number of hydrogen, it makes B more substituted. That's why B is the most stable product. That's the first thing I want you guys to remember. Now, in a lab, it's possible for us to determine uh, to run the reaction under certain conditions that will favor the formation of a thermodynamic product, or run the reaction in the conditions that will favor the formation of a kinetic product. So whenever you are running a reaction, your thermodynamic product can be the major product, or your kinetics product can be the major product. First thing I want you to remember is that major product does not necessarily means more stable. That's what you need to keep in mind. The major product does not necessarily mean the more stable product. The major product depends usually on the reaction condition. So for example, if you run the same reaction at low temperature, okay, if we run the reaction at low temperature, you'll notice that the kinetic product is the major product. That's the first thing I want you guys to take note. This is our kinetic product. And you can see with this reaction, we have up to 80% of the kinetic product formed. So low temperature favors the kinetic product. And consequently, we'll be able to also say that running the reaction at high temperature favors the thermodynamic product.
Would that mean that the reaction is also reversible?
Say that again.
Would that mean that the reaction is also reversible?
Yes, that's the next observation I wanted to make. That was the next observation I wanted to make here. So one thing I want you guys also, the first thing I want you guys to remember is the reaction condition, the temperature, because that is something you can easily control, okay? High temperature, the major product is the most stable. The major product is the thermodynamic product. At low temperature, the major product is the kinetic product. Okay. Now the next thing I want you guys to observe is the way the reaction goes. Notice this arrow. You will see that it is a single arrow, a solid arrow, meaning that we are looking at a non-reversible reaction. Does that make sense? So that single arrow is an indication that we are looking at a non-reversible reaction. So usually non-reversible reaction favors a kinetic product. And if you look at the next slide, you want to do the same comparison over here. If you look at that, if you look at the next slide and look at this particular arrow, you will notice that it is reversible. And so reversible reaction favors the thermodynamic product. So those are the two conditions I will say. If a reaction is reversible, chances are that you will always form the thermodynamic product. If a reaction is non-reversible, chances are that you will form the kinetics product. If the reaction is at low temperature, you form the kinetics product. If the reaction is at high temperature, you form the thermodynamic product. Those are the take-home messages to distinguish between a kinetics and a thermodynamic product. So this slide is simply a recall of what we've just said. So with this slide, it says, if both reactions are irreversible, if the reactions are irreversible, then we're looking at a kinetic control reaction. The major product is a kinetic one. Okay, and if one of the reaction is reversible, then we are looking at a thermodynamic product. That's basically what we've discussed. Does that make sense up to this point, guys? Perfect. Again, why is the 1,4 product a thermodynamic product? We've discussed that already. The 1,4 is a thermodynamic product because it is the most stable alkane. Okay, this is just a recap of what we've discussed in the previous slide. Okay, most stable alkane because the double bond over here is more substituted. Okay, more substituted, and this double bond is less substituted. So the more substituted the double bond is, the more stable that double bond will be, and that's what we'll refer to as a thermodynamic product. As a general rule of thumb, the 1,2 addition product is always our kinetic product. Always. Does that make sense? So whenever you have a 1,2 product, just be sure that that's your kinetic product. But then the 1,4 addition is not necessarily the thermodynamic product. That's what I want you guys to keep in mind. So be careful with that. The 1,2 is always the kinetic product, but the 1,4 is not necessarily the kinetic product. Okay. Now we need to understand why the 1,2 product is the kinetic product. That's what we need to do. We need to understand why the 1,2 is a kinetic product. And to understand why the 1,2 is a kinetic product, we need to think about the reaction mechanism as usual. I always talk about that. We need to think about the reaction mechanism. So if we have our reaction mechanism like this, this is our carbon 1, carbon 2, carbon 3, and carbon number 4. According to the reaction mechanism, the electron attacks hydrogen here, and this goes over there. So next thing you will form will be that with positive charge here. So that's your carbocation. That's the carbocation you will form. Okay, if you are intermediate, that will be the carbocation plus the Br minus. Now, notice that the carbocation you have formed can easily undergo resonance. I want everyone to see that. The carbocation you have formed can easily undergo resonance. And it can undergo resonance because we have our X, Y, and Z system. That's why it can undergo resonance. And so if you decide to now do the resonance, that will be the resonance structure. I hope everyone can see that. Please, if there is something you don't understand or you are kind of lost somewhere, feel free to interrupt me, okay? Don't just listen. And those who just turn off the class and they are still in bed sleeping, I can see you guys. So don't sleep. Okay, so that's the resonance structure. Now, what happened is the bromine is closer to the carbocation of the 1,2 addition. That's what we refer to as a proximity effect. Okay, so in this reaction, bromine being close to this positive charge can easily connect to that, compared to the fact that bromine will have to migrate a long distance in order to reach over here to give you the thermodynamic product. Remember that kinetics product has to do with distance. It has to do with speed. If the distance is short, then it's easier for it to reach there compared to a longer distance. That's what kinetics has to do with speed. Does that make sense? So the carbocation that is formed first has a chance of reacting first before the carbocation that has to undergo a rearrangement. The time taken for it to undergo the resonance, that's what disadvantages the thermodynamic product. I hope that makes sense. And so due to proximity, the Br minus is closer to carbon number 2 than it is to carbon number 4. And because it's closer to carbon number 2, it reacts faster with carbon number 2. That's why we have a kinetics product. That has to do with speed. Okay? So the kinetic product is always the one that forms faster. Okay, just like I said before, although the 1,2 product is always a kinetic product, it's not safe to assume that 1,4 product will always be a thermodynamic product. Okay, because remember, thermodynamic has to do with stability. If your 1,2 product ends up being the most stable, then that product is also your thermodynamic product. Look at the example we have here. We're looking at 4-methyl-1,3-pentadiene. This is our carbon 1, carbon 2, carbon 3, and carbon number 4 over here. Okay, and so when you run the reaction, this is over here the 1,2 addition product. Oh, I don't know why this thing is having difficulty. This is a 1,2 addition product, and over here that's the 1,4 addition product. So what I want you guys to take note is that if you compare the stability, of the 1,2 addition product to the stability of the 1,4 addition product in terms of their double bonds, that's what I want us to focus on. In terms of the double bond, you will notice that this double bond is more, substituted. And you will notice that this double bond is less substituted. Does that make sense? And so because this double bond is more substituted, it becomes the thermodynamic product. Because this is a 1,2 addition, it is the kinetic product. Does that make sense? So this is an example.
Substituted.
Say that again.
Why is that one more substituted?
Why is the one circle in blue more substituted? Again, let's go back and focus on the double bond. Compare these are the 2 carbons involved with the formation of the double bond. How many hydrogens are directly connected to that double bond? Can you answer the question?
1.
1. If we do the same thing with the red structure, the structural circle in red, how many hydrogens are directly involved with that double bond?
Oh, okay, 2.
2. So the one with fewer hydrogen means more substituted. Does that make sense? And so the blue structure is our thermodynamic structure. And because the blue structure is a 1,2 addition, it is our kinetic product. And so this is an example where the kinetic product is exactly the same as the thermodynamic product. I hope that makes sense for everyone now. This is another case study here. This is another case study. In this particular case study, the kinetic product and the thermodynamic product basically have the same stability. They basically have the same stability. And how do I know that? If I look at the carbons that are involved in the formation of the double bond, over here we have two hydrogens involved in the formation of that double bond, and over here, oops, and over here, if I look at this carbon, I also notice that I have two hydrogens involved in the formation. And so in this case, the 1,2 addition product and the 1,4 addition product are the same. They have similar stability. So you cannot say that one is thermodynamic and the other one is not. In this case, both of them will be thermodynamics. And so you can only distinguish which one is a kinetic product. And the kinetic product is the one that forms fastest. And the 1,2 is always the kinetics. Does that make sense? So everything depends on the situation you have at hand. Always observe the situation before you make a decision. Always observe the situation before you make a decision. So if we want to summarize what we've done so far, is that the 1,2 is always a kinetic product as a summary. The thermodynamic product is related to stability. The more stable product is always the thermodynamic product. Kinetics products are favored under low temperatures, whereas thermodynamic products are favored under high temperature. The kinetics product always proceed with irreversible reactions, whereas the thermodynamic product are favored with reversible reaction. That's what you guys need to keep in mind. And to be able to know which product is kinetic and thermodynamic, a notion of the mechanism is important for you guys. Knowing the mechanism is important. Now, let's have a practice problem. Let me give you guys this short practice problem and let's see. So let's create a poll with a question we have here. So the answer, I have A, I have B, I'm adding my choices. Say that again.
They want to know if the products are equally substituted. Does that mean there's no thermodynamic product?
If the substitution are the same, then they have the same stability. In that case, you cannot say one is thermodynamic. It's not possible because they have the same substitution. Does that make sense? So I have the pool. Guys, go ahead and answer.
Hey, could you slide the poll out? See the question?
Oh, yeah.
Yeah.
Let's see. Normally, this is weird. It looks like I can't move that pool.
You can always exit out of the poll and click back onto it later just to get it out of the way so you can see.
Oh, I can do that?
We can. No, the students can.
Okay. Then please direct him on what to do because it looks like I can't move the pool away. The pool only goes straight in the middle of the screen.
Dr. Zico, do you see our answers locked in? Because we can go and change them, but can you see when they...
Yeah, as you guys are responding, I can see it live.
Can you see this?
Well, I can see the number of times you change your mind.
Okay, good. That's what I was wondering.
Yes, it tells me the number of times you change your mind also. I see some people change their mind like 4 times.
Okay.
So the record is 5 times. So please take note. Put down the mechanism. Sorry, pH. pH stands for the phenyl ring, okay? The benzene ring. So this structure, this is how the structure will look like. So basically is all of this group that is referred to as pH. So maybe that will help. Is a whole group that's referred to as pH. Does that make sense? So maybe that will help some people change their mind. Please, the first quiz is for everyone. Because remember, I use the quiz as my attendance. Because I know some of you will connect and go back to bed. I know that. So if you don't participate in the quiz, then you haven't attended the class. That's for sure. And attending the quiz does not mean that you must have it correct. No. I don't want you to always have the correct answer. The most important, at least, is to participate in the quiz. But if you can participate at 100%, that would be nice, to be genuine with yourself. I'm still waiting for 9 responses. Okay, should we go ahead and answer it? Now I believe you guys can see your responses. So the correct answer here would be C. Which of the following product is a result of a 1,2 or 1,4 addition of HBr and is most stable? Okay, so C is the correct answer. Now, how do we arrive to C? How do we arrive to C? First thing we want to do is, let's look at the most stable. Let's look at the most stable. Which of these is the most stable? When I look at A, when I look at structure A, it will be interesting if we could draw the whole phenyl group. Okay, let me draw A out completely. That is a full structure for A. Okay, now if you look at A, you will notice that the double bond is not in conjugation with the ring. Do you see that? The double bond is not in conjugation with the ring. So that's why A cannot be the most stable. Let's proceed with that. A cannot be the most stable because of that. If you look at B, it will be the same problem. The double bond is very far from the ring, so they cannot be in conjugation. Same thing with D. The double bond is far away from the ring, so they cannot be in conjugation. So that's how we eliminate A, B, and D, because they can never be the most stable. And so we have choices to C and E. Does that make sense? We'll
Wait,
reduce the choices to
one
C and
close to the ring.
say that again.
The double bond has to be close to the ring.
Yes. The double bond has to close to the ring. It has to be close to the ring because if you look at this structure over here, the original structure, you notice that the double bond that is close to the ring is in conjugation with the ring. You remember what conjugation is? Alternation of double and single bond. I have a double bond. I have a single bond. I have a double bond, I have a single bond, double bond, single bond, double bond, single bond. So because of that conjugation, that's what brings about stability. Does-
Yes.
So the conjugation brings about stability. And so structure C and structure E are stable structure. Now, between structure C and E, we now want to find out if one of them is either a 1,2 or a 1,4. And over here, this is carbon 1, carbon 2, carbon 3, and carbon 4. Now, for a 1,2 and a 1,4 addition, carbon 1 must always have the hydrogen, irrespective. Does that make sense? Carbon 1 must always have the hydrogen. And when I look at structure E, this is carbon 1, carbon 2, carbon 3, carbon 4. You notice that carbon 1 doesn't have the hydrogen. Carbon 1 instead have the bromine. So that's what makes E out of the game. Whereas here, carbon 1 will have the hydrogen, carbon 2, carbon 3, and carbon 4. So structure C is a 1,2 addition, and structure is more stable because the double bond is in conjugation with the ring. Does that make sense, guys?
Why does the hydrogen have to be on carbon 1?
That's why we refer to it as a 1,2 addition. If you follow Markovnikov rules, why must the hydrogen be on carbon 1? According to Markovnikov rules, these are the two carbons involved in the formation of the double bond. Carbon 1 here will have 2 hydrogen, and carbon 2 will have 1 hydrogen. Markovnikov rule says that to those who have more shall be given. So according to Markovnikov rule, because carbon 1 has more hydrogen will be given to carbon 1. Does that make sense?
Yes.
Dr. Zico,
Yes.
can you explain the whole conjugation thing with the ring? Because I'm still not understanding what you meant.
Conjugation has to do with the alternation of double and single bond. So when you have a double bond that alternates with a single bond, that's conjugation. And the more conjugated the system is, the more stable that system will be. Okay. Now, if you look at the general structure, I want you to pay attention to this structure. If you look at the general structure of material, you will notice that you have an alternation of a double bond with a single bond, a double bond, single bond, single bond, and then you'll see you can continue that alternation like that. Do you see the alternation?
Yeah.
Yes. So double, single, double, single. And so basically now you now believe that if the double bond here is closer to the ring, then that double bond will participate in the alternation. That's basically what I mean by conjugation. And by virtue of that, only structure C and E has a double bond closer to the ring. Does that make sense?
Yeah.
Okay. Now let's try another question. I have another question for you guys. I have another polling question. That's the question, and then let me prepare the poll. So from Spain. So I have the poll up, guys. So let's see if you guys can attempt that one too.
Is the first one of the like options supposed to be like the kinetic? You know what I mean?
Which product are respectively kinetic and thermodynamic product? Well,
No, you see how like the answers there's like
yeah, the way the answers are arranged, yeah, I think one should be kinetics, and then the second one, the first one should be kinetic, the second one should be the thermodynamic.
okay.
Yes, yes. The first one should be kinetics, then the second one should be thermodynamic. So I have 8 students that are still missing. The responses are still missing. So I will have to stop the quiz like that. 7. So we shouldn't waste too much time on this quiz. Okay, so I believe you guys can see your responses. Pretty diverse, but I'm happy a lot of people had it correct. Okay, the majority of you had it correct. So, yeah, the correct choice here would be B. I will go with B. Again, how do we answer it? First thing, let's look for the thermodynamic product. The thermodynamic product will be the most substituted one. 1, 2, 3. I notice that 3 is more substituted. Does that make sense? I notice that 3 is more substituted. So 3 will be my thermodynamic product. And by doing that, ACE are out of the game because the thermodynamic product will be the second one. Okay, so the choices now are limited to B and D because they all have 3 as their thermodynamic. Does that make sense for everyone?
Wait, why is 3 more substituted?
Again, same thing. Why is 3 more substituted? If I look at the carbon involved in the formation of the double bond, with these particular carbons, I have 0 hydrogens involved in that double bond. Whereas if you look at 1 and 2, you will notice that in each case, you have 1 hydrogens. So the one with 0 hydrogen is more substituted.
Oh, so if it has less hydrogens, it's more substituted.
The less number of hydrogen involved in the double bond, the more substituted. So that's why 3 is our thermodynamic product. Now, we need to decide which one is our kinetic product. Okay, 1 or 2. And to decide which one is a kinetic product is through the reaction mechanism or through observation. This is my carbon number 1, that's carbon number 2, carbon number 3, carbon number 4. Remember, I told you guys that the hydrogen always acts on carbon number 1. You always add the hydrogen on carbon number 1. And so if I want to label the carbon here, this will be my carbon 1, carbon 2, carbon 3, carbon 4. Carbon 1, carbon 2, carbon 3, carbon 4. Carbon 1, well, there has been a change over here. Let's forget about 3. Let's only look at 1 and 2. So when you look at 1 and 2, you notice that in structure 2, the hydrogen was not added on carbon number 1. Does that make sense? But in structure 1, the hydrogen effectively was added on carbon number 1. And so that's why structure 1 is the kinetics product. And so D is not.
When I was doing it, I counted number 2 like in the reverse direction so that 1 could be 4. You know what I'm saying?
Yeah, I see what you are talking about. So if you counter it as 1, 2, 3, 4, you see have a problem. Your number 1 to have a hydrogen. You see that you haven't added the hydrogen on your number 1. Do you see what I mean?
Wait, what?
Can you see the orange labeling?
Yes.
With the orange labeling, this is 1, 2, 3, and 4.
Mm-hmm.
Is that the way you label it?
Yes.
But yet, you notice that your number 1 with the orange doesn't have a hydrogen, an extra hydrogen. Do you see that? You haven't added an extra hydrogen on number 1.
Oh, okay, okay. Yeah.
Yeah. So even if you count that way, it will not work.
If there was another hydrogen, then the double bond would be gone, right?
Yes, yes. Counting that way works with number 3. Look, 1, 2, 3, 4. And you see that number 1, you've added a hydrogen on that one.
Okay, can you show like the mechanism to get number 3?
The mechanism to have number 3, if you do the mechanism of this reaction, so that's what you have, right? That's your carbocation. And you notice that my carbocation, I have my X, my Y, and my Z. So because I have that X, Y, Z, I can undergo resonance. So if I undergo resonance, that's what I will have. And by doing that, this will be the resonance structure here. Do you see that? And so it is this second resonance structure that leads to the formation of number 3. And this first resonance structure leads to the formation of number 1.
Dr. Zico,
Yes.
going back to nomenclature for the reactant, why wouldn't 1 be the carbon with the methyl group? Since you want the lower number to have like.
But at the same time, you want the substitution, you want the double bond to have the lowest number. First thing, the double bond has priority over the substitution. So you want
Right,
to.
but you still have 1 if you put 1 at the methyl group and then 2
So
next to
what
it.
you mean? Yeah, if I put 1 here, right, and then put 2 here, that's what you mean.
No, switch 1 and 2.
Switch 1 and 2.
Mm-hmm.
I put 1 here and I put 2 over there.
No, put 1 where you have it and 2 to the left.
And 2 to the left here.
Yes.
Then this will be 3. That will be 4. This will be 5.
Oh, okay.
You see that this double bond that initially was number 4, now you are giving him number 5.
Right, okay.
Does that make sense?
Yes, perfect. Thank you.
Yeah. Okay, so that is all I want you guys to know about the kinetics versus thermodynamic product. Now we are moving on to a different type of reactions that conjugated system can do. And the type of reaction we'll be looking at is, yes.
Does the BR proximity to the double bond affect thermodynamics?
Say that again.
Does like BR proximity to the double bond affect the thermodynamics?
Well, the proximity is always what gives you the kinetic product. Okay. Now, the thermodynamic only has to do with the stability of the product. That's basically what I want you guys to remember here. The most stable product is always a thermodynamic product, which can sometimes be also the kinetics product. I don't know if I answer your question.
Yeah, you did. Thank you.
So with that, we are done with thermodynamics versus kinetics. So we're moving into a completely different type of reaction. That's called a Diels-Alder reaction. Okay. So in a Diels-Alder reaction, it's a reaction between a conjugated system. You remember what a conjugated system, alternation of double, single, double bond. That's what we call a conjugated system. So the Diels-Alder reaction is a reaction between a conjugated system, which is always referred to as a diene, that react with what we call a dienophile. Philic, the name phile, stands for love. So a dienophile means something that loves to react with the diene. Okay, so that's a typical Diels-Alder reaction. A reaction between a conjugated diene and a dienophile. And That reaction always leads to the formation of a cyclic system, a six-member ring. That's what the Diels-Alder reaction is. So what I want you guys to understand here is how does a Diels-Alder reaction form and what product are we going to obtain. That's basically it. Okay. Now, in terms of the mechanism of the Diels-Alder reaction, the electrons from the dienophile migrate and connect to one of the carbons of the diene. Then there is a rearrangement of the pi electrons that leads to the formation of a new bond between the diene and the dienophile. So that's what the mechanism for the Diels-Alder reaction is. It goes through a transition state, and then you now form your product. Now, a couple of things I want us to do here. A couple of observations. Let's look at the diene. This is my diene here. I want us to pay attention to the diene. How many pi electrons are involved? It says there are 4 pi electrons involved here. And the 4 pi electrons, you have 2 of them here and 2 of them here. That's what gives you a total of 4 pi electrons. So your diene will always have 4 pi electrons. Now, your dienophile here will have 2 pi electrons. Does that make sense? And that's why this reaction is referred to as a 4+2 reaction. Is that okay, guys? We refer to it as a 4+2 reaction because we have 4 electrons from the diene and 2 electrons from the dienophile. It is called a 4+2 cycloaddition. Cyclo means that we are forming a cyclic system. Addition because we are combining 2 components to form 1. Does that make sense?
Dr. Zito, is
Yes.
the arrow coming from the conjugated diene that goes to the dienophile, is that going to that carbon or is that going back to the bond?
It goes to a carbon.
Okay.
Yeah. So that's the first thing I want you guys to take note. Now, second thing I want us to do is let's label. Let's do some labeling. If I call this carbon 1, carbon 2, carbon 3, and carbon 4, okay? And over here, I will call this one carbon A and call this one carbon B. Does that make sense? Now, the first thing I want you guys to keep in mind is that in a Diels-Alder reaction, you are always creating a new bond between carbon A of the dienophile and carbon 1 of the diene. So you are creating a new bond. That's the first thing. Create a new bond between carbon 1 and carbon A. The second observation is that you create, does it have an E at the end? I don't know. That's not important. Create a new pi bond between carbon 2 and carbon 3. You can observe that. Look at the product. And then the third observation I want you guys to note is that you create a new bond between carbon 4 and carbon B. Those are the 3 observations that I want you guys to see. And let's do those. Over here, this will be my carbon 1, carbon 2, carbon 3, carbon 4. And this will be carbon A, and that will be carbon B. Now, create a new bond between carbon 1 and carbon A. You can see that's the new bond between carbon 1 and carbon A. Create a pi bond between carbon 2 and carbon 3. You can see over here, that's the pi bond between carbon 2 and carbon 3. Then create a new bond between carbon 4 and carbon B. That's the new bond between carbon 4 and carbon B. That's what the Diels-Alder reaction is all about. That's basically what the Diels-Alder reaction is all about. Okay. The Diels-Alder reaction also can be referred to as a 1,4 addition reaction. It's an example of a 1,4 addition reaction. If you label the carbon 1, 2, 3, 4, you will notice that you've added a group to carbon number 1 and you've added a group to carbon number 4. That's why it's referred to as a 1,4 addition reaction. Okay, so you can refer to it as a 4+2 cycle addition, or you can refer to it as a 1,4 addition reaction. That's what you need to know. Now,
Okay, Dr. Zico.
yes,
Okay, since it's a 1,4 addition, would this the Diels-Alder whatever reaction? Will it create the thermodynamic product?
with the Diels-Alder reaction, we don't really bother about forming the thermodynamic or the kinetics product because you only have one type of product that will be formed. You worry
Okay.
about a kinetics product or thermodynamic if you have two products that are formed with different stability. But here you only have one product that will be formed. Now, next thing I want you guys to note is that electron withdrawing group increases the reactivity of your electrophile. Okay, electron withdrawing group. You remember what electron withdrawing group are. If you don't know, then I will really recommend you guys to go and watch the 10-minute video I posted. That will really help you distinguish what an electron withdrawing group is. And the carbonyl is usually an electron withdrawing group. So this electron withdrawing group technically activates your dienophile. The dienophile is, in other words, the electrophile. So the electron withdrawing group will activate your dienophile because it will create this kind of resonance structure, and it will cause the dienophile to have a positive charge. That's what we refer to activating the dienophile, by creating that positive charge. So if you want your Diels-Alder reaction to work faster, you need to have an electron withdrawing group connected to the dienophile. That's basically the take-home message of this slide. Okay, for the Diels-Alder reaction to move faster, an electron withdrawing group needs to be connected to the dienophile. And so these are some examples of dienophiles with electron withdrawing group connected to them. This first dienophile doesn't have any group connected to it. This other dienophile has a carbonyl as electron withdrawing group, so this is more activated. Then this other dienophile has a cyano group, a CN group connected to it, so this dienophile is also activated. Does that make sense? So a couple of reactions, a couple of Diels-Alder reactions, some examples over here. In this our Diels-Alder reaction, this is our diene, and this is a dienophile. That's a dienophile. No matter how complicated this thing can be, I want you guys to take it simple. Let's label the diene: carbon 1, carbon 2, carbon 3, and carbon 4. And now let's label the dienophile. Labeling the dienophile, this will be carbon A and that will be carbon B. That's all we're interested in. The remaining parts of the dienophile remain unchanged. And you will notice that the remaining part of the dienophile are electron withdrawing group. And so according to the Diels-Alder reaction, you create a new bond between carbon A and carbon 1. You form a double bond between carbon 2 and carbon 3. And you create a new bond between carbon 4 and carbon B. So this is my carbon A and my carbon B. And this will be carbon 1. This will be carbon 1, carbon 2, carbon 3, carbon 4. So I create a new bond between 1 and A. I create a double bond between 2 and 3. And I create a new bond between 4 and 1. That's how I get to my product. That's how I get to my product. A triple bond can also act as a dienophile. A triple bond can also act as a dienophile. And if the triple bond acts as a dienophile, your dienophile is always labeled A and B. That's the dienophile. Always labeled A and B. And the diene is labeled 1, 2, 3, and 4. That's always it. And so you will create a bond between 1 and A. You will form a new double bond between 2 and 3. And then you create a bond between 4 and B. And so if you do that, This will be your 1, your 2, your 3, and your 4. And in this case, that will be carbon A and that will be carbon B. Does that make sense? And one thing you need to know is that the bond AB always end up with one fewer bond. Initially, AB here was a double bond. It ended up as a single bond. Here, AB was a triple bond. It ends up as a double bond. So you always have one bond less for AB. Does that make sense, guys? That's the first thing. That's the next thing I want you guys to take note of. Now, in terms of the molecular orbital, if you remember, we drew this molecular orbital sometime in class. And somebody asked me, why is this important? This is where the molecular orbital becomes important. If you draw the molecular orbital of your diene and the molecular orbital of your dienophile, this is the molecular orbital of the diene. In the molecular orbital of the diene, we look at one of the orbital called the HOMO, highest occupied molecular orbital. I talked to you about that. The HOMO of the diene will interact with the LUMO of the dienophile, and they need to have the same type of symmetry. They need to have the same type of symmetry. So here, because the symmetry are the same, these two orbitals will interact. Here, the symmetry are the same, the two orbitals will interact. Does that make sense? And it's the same thing here. If you use the HOMO of the dienophile and the LUMO of the diene, so long as the symmetry are the same, there will be an interaction. And that interaction is what leads to the formation of the bond. The interaction is what leads to the formation of the bond. That's what I want you guys to keep in mind. Any questions so
Excuse me,
far?
Dr. Zico.
Yes.
You said the interaction between the LUMO and the HOMO makes what bond again?
Is the interaction between the HOMO and the LUMO is what is responsible for the formation of the new bond. Remember here, we are creating a new bond between 1 and A and 4 and B. And so those new bonds, these are them here. These are the new bonds here.
Okay, and that leads to the formation of your
product.
Okay, of which one is it, the new pi bond between 4 and B, 2 and 3, or 1 and A?
In this case, this will be my 1, 2, 3, 4, and this will be my A and my B. So you are creating a new bond between 1 and A and a new bond between 4 and B.
Okay, and then does it, and I know that's probably not always the case, but it just so happens that that's the case in this point?
No, for all Diels-Alder reaction, it's always the case.
Okay,
in terms
so
of molecular orbital.
the interaction between LUMO and HOMO is always be responsible for the 1A and the 4B?
Yes, always.
Okay. Right.
Yes, always. Now, before we continue with Diels-Alder reaction, there's some terminology I want us to understand here. The diene will form two conformations. There are usually two conformations for the diene. There's what we call the S-trans conformation and the S-cis conformation. Trans, you know what trans means? Trans means the big groups are in opposite direction. So this technically is not a trans structure. That's why it is referred to as S-trans. Because a trans structure is about a double bond. Whereas here, we are looking at it about a single bond. If you look at that particular single bond, you will notice that the bulky group are arranged trans to each other. But a normal trans structure, everything is about a double bond. So this is why we refer to this as an S-trans structure, because it's technically not a trans, but it looks like a trans structure. Okay, and like a trans structure, the S-trans structure is more stable than the S-cis structure. This is technically not a cis because a normal cis structure is about a double bond. But here, if you notice, this is very similar to a cis structure. That's why we refer to it as an S-cis structure. And the S-cis structure is not very stable because the two hydrogens here are in close proximity, and so that can bring in what we call steric strain that destabilizes that structure. But then, for a Diels-Alder reaction to take place, take note, for a Diels-Alder reaction to take place, your molecule must be in the S-cis conformation. Molecule in the S-trans conformation cannot undergo a Diels-Alder reaction. Does that make sense? Only molecule in the S-cis conformation can undergo the Diels-Alder reaction. Okay. And so in this other
I'm sorry.
example here,
Excuse me.
yes, sir.
You said in the molecules in the S-cis can never undergo Diels-Alder?
No, molecule in the S-trans can never undergo Diels-Alder.
Okay.
Only the S-cis can undergo the Diels-Alder. Does that make sense? And so
Yeah.
in this other example here, if you look at this molecule here, this molecule is locked. This molecule is locked in the S-trans conformation. And because it is locked in the S-trans conformation, there will be no reaction. Does that make sense? Locked in the S-trans, no reaction. And over here, if you look at this other molecule here, the molecule is locked in the S-cis conformation. And so there will be a reaction. So this molecule is highly reactive because it is locked in the S-cis conformation. Does that make sense? I have another pooling for you guys. I like this. It makes Dr. Zico, so stupid. I will not do it. I gave you guys the answer already. No, let me do it again. Let me do it again. I know some of you were not paying attention. Let's take this pool before we can close. Okay, so God. Yes, most of you have it correct. Thank you. I like it. That looks good. So D will be our correct structure because D is the only structure that is locked in the S-cis conformation. Only the S-cis conformation can undergo Diels-Alder reaction. A will not because this is the S-trans. This is also S-trans. This is also S trans. This is not even a dienophile. So the only correct one will be D. Does that make sense? Let's try this one here. I have another one. Remember, you need to label it. Label it as 1, 2, 3, 4, and then A and B. Then connect them. That's what will help you find out which is the correct structure. For this one now, I will only take two answers as being correct, and then we'll discuss it in detail next class. This is just to give you guys a hint of what we'll be discussing next class to finish chapter 8. Wow. I can see how you guys are so diverse with your answers. Okay, so let's stop the polling here and let's try to discuss this. Okay, over here, this is my 1, that's my 2, that's my 3, and this is my 4. Then if I call this to be, what I would do is that, yeah, it might feel a little bit disappointed for you. I will call this one A and call this one B. And I will tell you why I do that. I will call this A and then call that B. You see, I have reversed it from what we used to do. I have reversed it from what we used to do. And I did that because I'll explain it next time in the future. So I will definitely have to create a bond between 1 and A, and then create a bond between 4 and B, and then put a bond between 2 and 3. So if I have to look at my 1 and A, over here, this is 1, that's 2, that's 3, that's 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. But now I need to find out which one is A, which one is B. And in this case, this would be my A and that would be my B. Does that make sense? Because the A is the one with the methyl group, B is the one with that big group. Okay, and so here, this will be my B and this will be my A. In this case, this is my A, that's my B. In this case, this will be B and that will be A, and this will be A and that will be B. So usually we create a bond between 1 and A. So if we create a bond between 1 and A, this is correct, and this is correct. So by virtue of the fact that we always create a bond between 1 and A, this is wrong and that is wrong. So any one of you who has A, C, and E as the correct answer at this stage, you guys are correct. At this stage, you guys are correct. Next class will see which one is the exact correct answer after next class. Does that make sense? So at this stage, I will accept A, C, and E. Any question before we close?
Dr. Nico,
Yes.
what's going on with lab today?
Oh yes, concerning the lab, we are meeting at what time is it? 2 o'clock. I will put a poggle. You guys will have a poggle to do, and the poggle will be during the lab time. So I will be connected at 2 o'clock, same way, but under the lab blackboard. You all go to the lab blackboard and connect yourself. I will be there, and then I will post a poggle. I will be ready to answer your question, any question you have for the poggle. That's what we're doing. That's what we'll do today for the lab.
So how are we gonna upload it or whatever?
The poggle.
Yeah.
Well, I don't know. You probably print it out, write it, and then upload it, and then take a picture and upload it.
Okay.
Okay, any question? Great. If we have no question, I really thank you for your participation. And please, please, office hours are there. Office hours are there. Make use of them. If I'm not in the office hour, send me an email. Send me an email,
Dr.
maybe 30
Nico,
minutes. Yes.
for the homework, it still says that it's due like March 1st and it won't let me open it.
Wow, that's weird. I thought I changed it. I will change it. I will look at it. I'm very sure I changed it. I will look at it. I will look
All
at
right.
it. Don't worry about that one. Yeah.
All right, thank you.
So the office hours are still there, guys. If I'm not there, send me an email.
Dr. Zeke, what time are your office hours today?
Well, today I'm very tired. I have a master defense to attend. But anytime that you need an office hours, just send me an email maybe an hour or two before, and then tell me that okay, at this time I want to meet, and I will be available, even if it's out of the hours that we have scheduled.
All right. Thank you.
Yes. Okay. Bye bye to everyone.